and welcome everyone. Over the next 50 or so minutes, I would like to talk about our experience with building a brand new operating system from scratch and the role that LLVM played in that experience. If you've been following the technical news, you may have noticed that a few months ago, we actually made a big announcement. We've announced that Google will be launching Fuchsia OS to the first device, the Google Nest Hub. Some of you may have also noticed that many of the news articles have featured tweet I made. This wasn't part of some deliberate plan. I was simply too excited that it would be a final ship. And when we lifted the curtain, I made this tweet. I went to bed, and when I woke up in the morning, I found out that not only my notifications have exploded, but I also had 1,500 new followers on Twitter. And this was a very brief experience with internet fame, and it was one of many lessons that I've learned while working on this project. I joined Google in 2015, and after a very short stint on the native client team, I have joined Fuchsia, where I've worked on many different things over the years, including our build system, our infrastructure, but most importantly, the Fuchsia's Clang toolchain that I'm now primarily responsible for together with a large group of people. Related to Adelina's talk and workshop, I think it may be also worth pointing out that I don't have a compiler background. I've started contributing to LLVM after joining Google, primarily to meet our goal of providing great toolchain for Fuchsia. And I'm still doing so, not only because we are not done yet, but also because I really enjoy working in this community. The first change related to Fuchsia that I sent out to LLVM, you can see it here on the slide, was fairly underwhelming. It just introduced a new triple to support Fuchsia as an operating system. The second change, though, is more interesting. The description actually mentions a couple of different things. It says that Fuchsia uses compiler-t as frontline library, libc++, libc++ ABI, and unwind as the C++ library. And we use LLD as the default linker together with the integrated assembler. Now, mentioning this now probably wouldn't surprise anybody. It's not very exciting. There are many other projects, many other toolchains that use the same exact setup. But you have to take into the fact that this was back in 2016. And at that point, LLD could barely just link itself. So this choice was not only forward-looking, it was also very optimistic and perhaps even a little bit naive. There are still many issues, and it was a very rocky road. But we were optimistic that with enough effort, we can get to the point where Clang toolchain will be usable for all of Fuchsia. Initially, though, it was only used for our user space, and getting it to build and link a kernel took a lot of effort. We had to put in a lot of improvements into the linker script support, which is really important in a low level and embedded. We had to implement a number of new features to better match the functionality of GNU linkers. We had to address a number of issues. We also had to build entirely new tools from scratch as replacement for their GNU counterparts. This includes LLVM object copy and LLVM strip. But it all went well, and the driver, Clang Fuchsia driver, landed in October of 2016, and in April of 2017, LLD could already link our kernel. And by the end of the year, we've managed to completely replace all GNU binutils in our toolchain, and at that point, we had a pure LLVM Clang toolchain. It took another 18 months for Clang to become the default compiler for the entire system. And at this point, you may be wondering why so long when we already had a functional and usable toolchain at the end of 2017. Well, it wasn't just technical reasons. LLVM had to prove itself. We've been previously using GCC for our kernel, and the fact is that GCC has been around for decades. Developers have a lot of trust in it, and it's especially true in embedded low-level development like kernel. We had plenty of evidence that Clang is ready. After all, it's been already used for Google production. It is being used by Chrome and Android. But there are still many aspects that are important to embed it that were missing, like better assembly support, linker script support, binary tools, and so on. So we actually had to do a lot of work behind the scenes to convince everyone on our team that LLVM is really serious about embedded And many of the features and tools that LLVM provides, things like sanitizers and static analysis, can be of great benefit to kernel developers. This is also perhaps the biggest lessons that I've learned while working on this project, the importance of trust. Now, in the remainder of this talk, I'm going to go into more details, and I'll talk about how we brought LLVM to Fuchsia and how we've integrated it into our project. But first, I would like to give a very brief overview of the system, what it is, why do we feel a need to build a new system from scratch. And towards the end, we're also going to look at some of the problems that we would like to tackle in the future. So let's start with Fuchsia. What is it? It's an operating system, an open source operating system that prioritizes security, updatability, and performance. It was built from ground up, and it uses a new system design. We are opinionated about Fuchsia not being POSIX. This lets us explore ideas for what we hope is a more efficient and more secure design. It is what we call an internet-first operating system that's meant to be always up to date, enabling long support horizons, and it is focused on minimal resource usage. At the same time, we're not targeting embedded. We still want to provide a full user experience, and we target 64-bit CPUs only and Vulkan-capable GPUs. And as I mentioned at the beginning, after 5 years of development, we started shipping Fuchsia to the public for the first time this year on the Google Nest Hub device, which is depicted here on the slide. With Fuchsia, we're trying to address challenges of the current operating system paradigm as we saw them when we started. We are now seeing explosion of more connected, always-on devices that live in our private settings and thus have greater need for privacy and security. The Google Nest Hub is actually an example of such a device. Keeping these devices up to date, keeping them secure, requires ongoing investments, but that can sometimes reduce product lifespan. Also, every different form factor typically requires a fork of the operating system, and that can be costly to maintain. And our hope is we can address many of these issues with Fuchsia. To address them, we've decided on an architecture that's based on 4 main principles, which is security, updatability, inclusivity, and pragmatism. Now, software on Fuchsia always has the least privilege it needs to perform its job. On Fuchsia, there is no ambient authority. All software components can only interact with the objects that they have been given explicit access to, and software isolation is enforced directly by the kernel. So there's typically no need for additional security mechanisms like sandboxing, although developers are welcome to implement those if they feel a need for. Keeping your software up to date is an important security practice, and that's why we've designed a system for software components to be independently updatable. We draw a lot of inspiration from the web, and software on Fuchsia is designed to come and go as needed. The system has lots of mechanisms to ensure updatability. This includes hermetic packaging, versioning, evolution affordances for protocols, and so on. Fuchsia is also inclusive, and that's not just for its community, but also for its architecture. The system is runtime and language agnostic. Developers are free to choose whatever runtime and language is best for their product. And Fuchsia is open source. It is developed in the public under a permissive license and with a public governance model, and all developers are welcome to come in and contribute. Finally, I would say that Fuchsia is not a playground for experimental operating system concepts. It is a production-grade operating system, not a research project, and it is designed to power real consumer devices and therefore must adhere to fundamentals like performance. Our roadmap is driven by practical use cases. We derive a lot of our requirements from our partners and products needs. I mentioned architecture, so let's take a brief look at some of the key aspects of Fuchsia's architecture. First off, let's start off with Zircon, which is our capability-based object-oriented kernel. It is a pragmatic message-passing kernel, but unlike what you may have heard or seen, it is not a microkernel. We apply many of the concepts that were popularized by microkernels, but we don't strive for minimality. For example, Zircon currently has over 170 system calls, which is vastly more than a traditional microkernel. And this goes back to the pragmatism principle. On Zircon, there's no global namespace. Capabilities and resources are passed around by opaque handles, not by names. This is important for security. And from the updatability perspective, we provide a binary stable driver interface, which allows kernel to be updated independently from drivers, which are just regular user-space processes. And it's not just drivers. There are many other components that on traditional operating systems are part of the kernel, but in Zircon, they live in user space. This includes things like user permissions, networking, file system, device drivers. What Zircon does provide is IPC, memory management, scheduling, and process management. Now, with all these components living in user space, there's great importance for having good IPC. And while Zircon provides the underlying primitives for doing IPC, like channels, we also provide a higher level ones. In particular, Fidl, which is our IPC protocol, wire format, and language, which allows language agnostic interactions between components that are written in different languages. This goes back to the inclusivity principle. We provide bindings for many different languages, which include C++, Rust, Dart, and more. And in Fuchsia, capabilities are expressed as Fidl protocols, which helps promote interchangeability and reusability. Now, the acronym Fidl stands for Fuchsia Interface Definition Language, and you can see what this language looks like here on the slide. It is a C-like syntax, and if you're familiar with protocols like protocol buffers, this should feel very familiar. This small example describes a simple protocol with one method. We also have tools built around this language, tools like Fidl Compiler, which is used to generate bindings, Fidl Format for formatting, and so on. You can use Fidl Compiler to generate bindings for different languages. So here in this small example, we have two processes, C++ client process talking to a Rust server process. And these use Fidl and Fidl bindings to serialize Fidl messages on to the Zircon channel. But even though I'm talking about processes here, when we talk about software on Fuchsia, we typically talk about components, which are the fundamental units of execution on Fuchsia. They are the isolated containers for software, and they must explicitly declare all capabilities that they use and they expose. If you're familiar with software containers from other systems, systems like Docker, this should feel familiar. On Fuchsia, all user-space software is a component, and that includes drivers, it includes system services like file systems, networking, and as well as user applications. Components always have the least privilege, and they only access information that they need to perform their job, which is really important for security. Components are defined in what we call CML, which is the component manifest language. We also have tools for processing this language. As you can see, we really like languages and language-related tools. Here's a small example of a simple component, which represents a unit test, a G-test unit test. So as you can see, even tests are components on Fuchsia. This test exposes one capability, which is the Fuchsia test suite. That's a protocol describing a test. And it uses two protocols, debug data, which we've seen on a previous slide, and logsync, which is used for logging information out. This component manifest is then used to instantiate a component. So here we have a small example, a little hierarchy. On the bottom left, we have my test component, which is test wrapper as a parent. There's archivist, which is exposing the logger interface implementation, and through test manager is also routed to debug data implementation. And component manager in Fuchsia is responsible for connecting and routing all these protocols between components. Now, if components are the units of execution, packages are units of distribution. So on Fuchsia, packages are hermetically sealed bundles of components and all related asset files. Again, if you're familiar with systems like Flatpak, this should feel very familiar. The main difference being that in Fuchsia, there is no global file system. Everything comes in packages, and every component only has visibility into its own package. Packages themselves are identified by URLs, and they can be downloaded, executed, and updated on demand as needed. Here's a little example where we have two different packages with two different tests. What is interesting here to note is that these packages use the same version of libc as the ld.so, but they use different versions of libc++, and that's not a problem. In Fuchsia, all of the binaries are stored in our blob file system, and they are identified by their content. There's no global file system. There's no single system libc++. So each of these packages has its own version of libc++, but they are going to share libc. This is actually one of the reasons why on Fuchsia we prefer dynamic linking over static linking, because that helps us deduplicate common functionality across packages and across components. And this was a very brief overview. We don't really have time to go into more details, but if you're interested, if you'd like to learn more, I would highly recommend visiting fuchsia.dev. We have a great Fuchsia fundamentals section that goes into far more details. It also has a lot of practical examples. At fuchsia.dev, you can also follow platform evolution by looking at our RFCs, and you can reach out to us at discuss@fuchsia.dev if you have questions. Now let's move on and let's talk about how we build Fuchsia. As you can probably imagine, building an operating system from ground up takes significant effort, and it was a significant effort. We decided from the beginning that we want to develop Fuchsia in the open. That meant that we could not reuse all of the great infrastructure that Google has, and instead we had to rebuild a lot of it ourselves. Let's first start with some numbers. Most of our code lives in a single Git repo, which currently has about 115,000 commits from 700 contributors, and it totals about 5 million lines of code. We also get close to 500 commits from 150 contributors per week. For contrast, LLVM has about 400,000 commits from about 2,000 contributors, and it totals to 22 million lines of code, depending on what tool you use to count. In LLVM, there's roughly 700 commits from 200 hours per week. So in terms of total size, Fuchsia is currently roughly 1/4 the size of LLVM, but in terms of the rate of development, these two projects are actually fairly close. In Fuchsia, we also rely on a number of third-party dependencies, and the full system checkout has over 100 Git repos. We use plenty of different languages to build Fuchsia. C++ is used primarily for bootloader, kernel, and device drivers. We use Rust for most of our user space components. We use Dart for UI through the Flutter framework, and our infrastructure is implemented primarily in Go and Python. Our Fuchsia SDK supports C++ and Dart, but we are hoping to expand a set of languages in the future. Now, we try to follow many of the best practices that are common across Google and other companies, including code reviews. Any change that goes into Fuchsia has to be reviewed by a code owner, and we use Gerrit for doing code reviews. We also have a set of plugins to aid the development. We use both pre-submit, post-submit testing, and we always run a combination of unit, integration, and end-to-end tests. For every change, we also perform a number of automated checks, including linting and formatting, and we use LLVM tools like Clang format to do so. Here is a little example. When you upload a change, you can trigger a number of pre-submit jobs, including static checks that I mentioned. Speaking of static checks and static analysis, we make great use of static analysis. We enable all warnings, and we turn all warnings into errors. And we try to adopt all new warnings as they're being introduced in Clang rather than trying to suppress them. We also use Clang Tidy, and we've actually built a number of Fuchsia-specific checks to enforce our own coding guidelines. We also use Static Analyzer, and we have also implemented custom checker to detect handle leaks and double closes, which we've used successfully in Fuchsia to find real bugs. Here's another example from Gerrit. Here you can see a message, a warning reported by Clang Tidy that's surfaced directly in Gerrit. Here is another example. This is a recent warning that was introduced to Clang to address the issue that affected Chrome OS a couple of months back. And as you can see here, it took us about 4 days from the point where the warning was introduced in Clang to the point where our code base was completely clean and this bug was closed. We can do this because Fuchsia is a fairly new code base. We don't have a lot of legacy, and we are always trying to keep our code base in motion. We also use source-based code coverage. We actually collect coverage for both C++ and Rust, and we do so both in pre-submit and post-submit testing. We expose both incremental and absolute coverage to developers, and that is done directly in Gerrit and in code search. We also warn developers when coverage of their changes is too low. And making this possible requires a lot of changes throughout LLVM, our infrastructure, our build, and involve a lot of people. Here's an example of what this looks like. When you upload a change to Gerrit, we run a set of tests, we call it coverage, and then we surface it directly. The lines on the left highlight which lines of dispatch were executed and which were not. So the reviewer can immediately tell how well you're doing on testing. In addition to coverage and testing, we also use sanitizers, and we absolutely love sanitizers. We sanitize everything we can, including the kernel, low-level parts like the libc, also our host tools. We use ASAN both in pre-submit and post-submit testing, and every test includes ASAN or KSAN, LSAN, and UBSAN. We are also bringing HUASAN now. We also encourage the use of coverage-guided fuzz testing, and we continuously fuzz our kernel using Zscaler. Again, getting here and making this possible took a significant effort from lots of people, and we are actually quite proud about this. We also eagerly adopt new security hardening features. We default to Pi, and we use ASLR everywhere. This is already pre-common standard practice. But we do more. We use automatic variable initialization to prevent the use of undefined memory. We use safe stack and shadow call stack by default to protect against return address overrides. And we use Scudo as our default system allocator to protect against heap-based vulnerabilities. On top of that, we are also increasing the use of Rust throughout our system. Now, this is what you would see as a regular Fuchsia developer, but I thought it may be also interesting to take a look behind the scenes and give you a little bit more insight into how we built all of this and what work it entailed. So our goal is to provide a modern, permissively licensed, self-contained toolchain with a complete set of tools. We want to support a broad range of both host and target platforms within a single toolchain. And our hope is to always leverage the ecosystem of tooling, like linters, formatters, static analysis, code coverage, sanitizers, everything I mentioned in between. And we chose LLVM in the early days of Fuchsia because we hope that LLVM can match all of these goals, and it did. There are also a number of LLVM teams at Google that we collaborate with, that we exchange ideas and share efforts with. We maintain our own Clang and REST toolchains for Fuchsia. This is because our goal is to provide the same exact experience on every supported platform. Our goal is to deliver a cross-compiling LLVM-based toolchain without any legacy component. We follow the live ahead model, and we release new toolchains on roughly a weekly cadence. Also, we don't carry any downstream patches. We develop all new features in upstream and then adopt these features once they become available. Closely following ahead and doing all of development in upstream allows for rapid adoption of new features, and it's also a way for us to provide fast feedback back to the LLVM and Rust communities. Speaking of Clang toolchain, we're trying to provide a complete C and C++ toolchain distribution that's based entirely on LLVM. It includes Clang, as well as a number of LLVM tools and runtime libraries. And we use it to build all of Fuchsia, everything from bootloader, which is a UEFI binary, to kernel, system libraries, user applications, and even host tools. It is also being used by a number of other related projects, such as Pigweed, Dart, and Flutter. At Google, it is used by hundreds of developers. There are also some developers using it outside, and there are thousands of automated builders that use it every day. I'm not going to go into more details about how we build a toolchain or how we distribute it. I've actually covered this in a talk that I gave earlier this year at the LLVM Distributors Conference. So if you'd like to see more details, I recommend watching that talk. Now, when we started, not all of that was possible because LLVM wasn't a complete tool chain, and it took quite a bit of effort to get there. There are many tools, many runtimes that developers now take for granted, but in many cases, we actually had to build those from scratch or adapt them to work on Fuchsia. From the beginning, we were co-developing the operating system and the toolchain, and we actually took that to our advantage, and we were often adapting the platform to the toolchain and its limitations. This actually made it easier for us to adopt many LLVM components even before they were ready for broader adoption. Example of this is integrated assembler. In some cases, we actually went in our kernel, we replaced the directives that weren't originally supported by the integrated assembler with their equivalents where we could, and that actually sped up our adoption of LLVM integrated assembler. We also had to do a lot of work to support building the complete cross-compiling toolchain. We needed a way to build all the runtimes in the right order with the just build Clang and LLVM tools. And we needed to install all those side by side and ship them as part of a single cross-compiling toolchain. Solving this required a lot of changes throughout the CMake build, throughout the Clang driver. I've went into more details on this in the talk that I gave at the LLVM Distributors Conference. So if you want to learn more, I would recommend watching the talk later. Now, as you probably already gathered from everything I've talked about so far, Fuchsia is not like the other operating systems. And many runtimes, especially compile-RT runtimes, make a lot of assumptions about the operating system, like always having file system available as a way to export and collect data. And these assumptions don't always hold for Fuchsia. So for example, here is a little snippet from the compile-RT profile runtime, which just uses file system. It does fopen to open a file and then write the data out. Now, this is not going to work on Fuchsia out of the box. Out of the box, fopen is going to return null, because on Fuchsia, there is no file system by default. Having an access to file system is a capability that you need to be granted, and not every process on Fuchsia has or should have access to file system. Now, there are ways around it. One, for example, is to use an libfdio library, which is shown here on the side, which is both an emulation of the file descriptor API, as well as the implementation of Fuchsia.io protocol. Fuchsia.io protocol describes the file system API, but that may not work in every case. For example, in Fuchsia, file systems are just regular usage-based programs. And therefore, we may want to use profile and coverage for file system. And that means that we cannot use file system to export the data. Also, Fuchsia.io is a fairly large protocol, and having that may be a lot of overhead. So the way we solved this was by introducing a small protocol. And it's actually the protocol that you've already seen earlier on the slide, which is called debug data. It's a very minimal protocol. It has just a few methods. So the most important one is publish, which can be used to take some collected data and just push them out together with a name. This protocol can be implemented purely in memory. You can even have multiple implementations. We actually have multiple implementations of this protocol throughout Fuchsia for different purposes. This protocol we've used successfully in the profile runtime, sanitizer coverage, X-ray. And it shows what is perhaps the native way of porting and building things on Fuchsia, rather than using these big, large interfaces, which have a lot of ambient authority. We're trying to design more narrow, more tailored protocols. Now, porting the existing compile-RT runtimes to Fuchsia require a lot of effort, a lot of different changes. First of all, as you can probably imagine, we had to factor out all the file system related code and make it possible to use mechanisms like Fuchsia.debug data. We also had to implement a number of OS abstractions, use Fuchsia counterparts where needed, and we had to do a number of refactorings. In many cases, we had to introduce additional abstractions, extract functionality. We also had to do a lot of refactorings in the sanitizer runtime to support offline symbolization, which is the default way of symbolizing on Fuchsia. Speaking of sanitizers, the way we chose for implementing or porting sanitizers to Fuchsia is quite different from other systems. Existing sanitizer runtimes were written for what I would consider hostile systems that you cannot easily change. But Fuchsia is a system that was designed with sanitizers in mind, and we always wanted to support sanitizers as first-class citizens from the very beginning. And to do so, we provide an internal API from our libc, which drastically simplified the sanitizer implementation and obviated the need for things like interceptors. And that actually allows us to instrument even things like the C library itself, as well as other runtime libraries like libc++. The same goes for SafeStack and Shadow Call Stack, which on other platforms requires runtimes, which may not always use the most efficient or most optimal implementation. But because we designed Fuchsia and lower parts of the system with these runtimes in mind, we could choose the optimal model. So in our case, SafeStack and Shadow Call Stack are supported directly in Fuchsia C library, and there is no compile RT runtime needed at all. Speaking of libc, we are actively adopting LLVM libc for Fuchsia. We've actually been involved in the LLVM libc proposal, and we've been working very closely with the LLVM libc team. We are very grateful for all the great collaboration we had with them so far. And we are now in the process of evolving our libc, and we're incrementally replacing parts of it with the LLVM libc counterparts as they become available. Now, I mentioned earlier in the talk that we care about the resource usage. This primarily entails binary size and memory, because the first products that are powered by Fuchsia have very limited storage space, limited memory, and we had to work pretty hard to make everything fit. For software that's built in the Fuchsia tree, we use ICF and GC sections, and we actually had to address a number of related issues, both in LLVM and LLD, especially in the early days of the project. We have also adopted the rel-r location packing format shortly after it became available in LLVM, and we use rel locations on all the architectures now. We've been also experimenting with the ML inliner. We're using a model that's trained on a Fuchsia code base to further reduce the size, and we are working closely with the team responsible for that work. Another technique that we use to reduce resource usage is relative vtables C++ ABI. We use it to replace 64-bit function pointers in vtables with the 32-bit PC relative offsets. And that not only let us cut the size of vtables in half, it also meant that we can move vtables into a read-only memory and then share them across processes, reducing the memory usage of the system. This is now the default C++ API on Fuchsia, and we could do this change because of this somewhat unique packaging model that we use on Fuchsia that I mentioned earlier, where different applications can have different versions of libc++. In an extreme case, every application can use a different C++ API, and it's not a problem at all. I'm not going to go into more details about how we've implemented this. Leo Chen from our team actually gave a talk at this conference. So if you're interested in learning more details, I would recommend watching his talk later. Speaking of ABI, this is also something that we care about. And so we built a tool that was originally called LLVM. Now it's called IFS, which is a tool that produces textual descriptions of the share library ABI, as well as linkable ELF shared objects. These textual descriptions can be used to compare APIs when you're making changes to libraries, and it makes them easy to spot and review directly in Gert. And the use of ELF stubs can reduce the incremental build time, because we can avoid relinking binaries if ABI of their dependence hasn't changed. Again, I'm not going to go into too many details about how we build this, how we use it. Hale, who from our team gave a quick talk yesterday at the LLVM Dev meeting. So if you're interested, I would recommend watching this talk later once it's available. So these were some of the features that we built. It's not all, because we just don't have time to get into everything. So I'm just going to briefly cover some of the other things that we worked on over the years. I've already mentioned LLVM Object Copy and LLVM Strip in the beginning. These are the drop-in replacements for GNU Object Copy and Strip that our team has built. We've expanded the address space attribute, and we've implemented no-diff attributes. In GNU world, these are provided by the sparse checker warning, by the sparse checker, but in Clang, they're supported directly, and we actually use these in our driver API, and they are used by our drivers. We've also built compiler RT replacements for some of the libgcc counterparts, like crtbegin.o and crtend.o. I also mentioned earlier that we've built a number of Fuchsia-specific Clang tidy checks, and some of those were later generalized, and they are now used by other projects like LLVM C. And there are more things that we have under development that we are working on and that are coming soon. We've been for a while working on the fixed point arithmetic C99 extension. This provides support for precise decimal calculations without using floating points. And it's something that we would also like to use in our drivers. We are working on rolling out Clang doc, which is the C and C++ documentation generator based on Clang that we've built. And we want to use it to generate documentation that's going to be on Fuchsia.dev. We are building an LLVM-based implementation of the debug infod protocol. It's called LLVM debug infod. And we're also working on a tool called Clang mix expect, which can be used to verify the correctness of built-in expect annotations. So these are all the things that we are already working on, but there are more things that we are thinking about and that we would like to do next. We've already shipped Fuchsia to millions of devices, but we don't feel like we're done. Actually, we feel like we're just getting started. In the future, we would like to evolve Fuchsia into a more general usable operating system. And we also hope that LLVM is going to be part of that. There are a couple of things that we have in mind. First of all, we need support for running LLVM runtime tests on Fuchsia. This is not something that we do today. We rely solely on end-to-end testing. We exercise all the code that was generated by LLVM. That's, after all, how we build all the code. It's part of LLVM. It's part of Fuchsia. We also check all the binaries that include LLVM runtime libraries when doing regular testing. But checking any changes going into LLVM requires building the entire system and running all the entire test suite. And that not only increases the cycle time, it also means that in the case of regression, our team is often responsible for doing all the triaging, debugging, and sometimes even fixing these issues, and that can be fairly toiling. So to address that, we would like to start running LLVM runtime tests directly in Fuchsia, but there are some of the things that we'll have to do to make it possible. Most importantly, we would like to improve support for cross-target testing inlet. This is not something that exists today. Some of the runtimes do have support for remotely executing tests, but it is implemented in what I would call an ad hoc way, and it can be inefficient and difficult to generalize. Also, many of these tests make assumptions that just don't hold for Fuchsia, and we will need to address that. Here's a small example of a test from the ASAN test suite. It does a couple of things. It uses Clang to compile a small test binary, then it runs it, then it generates a small suppression file, puts it into the environment, and then runs it again. The %run substitution that's highlighted is going to be actually used to insert custom executor, and then you can use it in theory to offload the execution of a test to a different device. But that's not as easy on Fuchsia, because if you remember, on Fuchsia, all the software comes in the form of a component and it has to be packaged up. So every time you use this %run substitution, we will need to generate the component manifest. We will need to package up this test and then push it onto the device. And it's not even clear to us right now if just by looking at the arguments passed to %run, we can gather all the requirements on information we need, for example, to generate the correct manifest that explicitly specifies all the capabilities that the test is going to need or all the files it's going to use. So addressing that might mean that we'll have to improve specifications of these tests to be more explicit. But there's another issue. Here you can see that these two run executions are actually independent. So in theory, they can be all done at the same time, but that's not what's going to happen. Like as it's described today, you would run test once, then you have to wait until it finishes execution, and then run the second one. So that can take a long time while your test is blocked and stuck waiting. So ideally, when possible, we would like to bundle up all these tests, batch them up, and execute them in chunks. But in order to do that, we would actually need to understand dependencies between different command invocations, build more of a execution or dependency graph, and that's not something that exists in lit today. And it's not just the LLVM runtime tests that we want to port over to Fuchsia. Eventually, we would also like to make Fuchsia an officially supported LLVM platform. There are many LLVM libraries, and super libraries already support Unix and Windows, but Fuchsia is neither of those. And while in some cases we could probably use emulation and we could use libraries like libfdio, we think that the emulation may not always be the optimal solution. It may not provide the best possible performance. Some of the interfaces also make assumption about the underlying system. The most common is the use of raw file descriptors or sockets. And ideally, what we would do is we would address those and replace those usages with proper abstractions. So we can actually replace those abstractions and use the appropriate fusion mechanisms. Now you may be wondering, why do we want to support LLVM on Fuchsia? We want to do it because LLVM is becoming increasingly more important. It's not just a framework used to build compilers anymore. You may have seen this in the keynote of our circuit, but there are many other things. For example, MLIR is already being used as a dependency of TensorFlow. And we are actually now seeing products that are powered by Fuchsia trying to use TensorFlow, which means that very soon we're actually going to need that support for Fuchsia in LLVM. And I expect that as the importance of LLVM is going to grow, so will grow the importance of supporting Fuchsia natively. But even beyond just supporting LLVM on Fuchsia, in the future, like I mentioned, we want to turn Fuchsia into a more generally usable operating system, and that means building software on Fuchsia. Eventually, we want to support the full software development cycle, which includes compilation and linking. But doing so efficiently may require some changes to the compiler organization to achieve the optimal performance. Like the use of threading instead of spinning up new processes would apply to Fuchsia as well. On Fuchsia, for example, we don't have fork. So anytime your performance is dependent on having a very fast process creation, copy and write semantics, fast startup time, the performance on Fuchsia may suffer. And I believe that making some of those changes, like the ones that were described in Alex's talk, can be also beneficial to other platforms, not just Fuchsia. And it's not just, I believe that we will need to make other changes. We might actually need to design an entirely new architecture for building software. The traditional Unix model for building software has served us well for decades, but we believe that it may be becoming a little bit dated, and is definitely not a good fit for Fuchsia, which prefers service architecture. And we think that using service architecture may not just be a better fit for Fuchsia. It may also help and improve performance on other platforms. This is something that was already brought up by Daniel Dunbar in his talk at the LLVM Dev meeting a few years ago, when he's actually shown an alternative architecture which was based more on what I would call service architecture. And he's demonstrated some really great improvements, like reduction in build times for Clang on the order of 80%. Now, implementing that vision may require significant refactorings and changes throughout LLVM. We may have to introduce new abstractions, but I believe that it's going to be worth it, not just for Fuchsia, but for LLVM overall. And in addition to LLVM, we may also need a new generation of build systems to support that, like the ones that Daniel mentioned in his talk. And I hope with all of those changes done, one day we will actually be able to use Clang on Fuchsia natively. Not as a subprocess that you spin up, but as a service through a protocol, which would be the native Fuchsia solution. So that's all I have for today. Thank you very much for watching. And I also want to use the opportunity to thank everyone who has contributed to our effort over the years. We wouldn't have made it without your help. I would also like to thank very much to the LLVM community. I mean, you're fantastic. We really appreciate your help, especially all the teams that we've collaborated with over the years and that we continue to collaborate with. And now I'm happy to take questions.
Okay, yeah, thanks for the presentation. So right now we have 10 questions, but we only have 5 minutes. So I just go through them really quick. So first question is that when you do the automatic variable initialization, do you use value 0 or other values?
So at the moment, we use pattern initialization. We did consider maybe only using pattern initialization in debug mode and then using 0 initialization in a release mode, but that's not something we've done. So far, using the pattern initialization hasn't been a problem in terms of performance for us.
Okay, thanks. Next question is, have you explored any form of CFI, like pointer authentication on ARC64?
It is on our roadmap. It's something that we definitely want to deploy. I think the main issue right now is that CFI relies on LTO, FinLTO, and that's not something that we have fully working on Fuchsia. We already can use LTO, FinLTO for user space, but we would also like to use LTO and FinLTO for the kernel, and that's where we believe that it might have the biggest impact. And the same goes for CFI. And there are actually a couple of issues, including some code gen issues that we've encountered when using LTO with our kernel. This is actually something that we are actively investigating. And I hope that we can make more progress both towards enabling LTO throughout the whole stack, as well as enabling CFI in the next year.
Okay, thanks. Next question. Do you use any unstable libc++ ABI?
So the ABI that we use for libc++ is the unstable one. Okay. So we just get changes as they keep landing in libc++, and because we are on this live-ahead model, that means that our libc++ ABI could be changing on a weekly basis. We are not even keeping track. This is actually something that's taken care of by our packaging model.
Okay, thanks. Another question is about static analysis. Is there any specific issue in using static analysis on OS compared to other general application program? Yeah, it's more like a question to me, actually.
Yeah, Huawei actually has done a lot of great work on static analysis. I don't think there's any specific issue with respect to the OS. I would say that Clang Static Analyzer does some modeling. It has some understanding of existing APIs like POSIX APIs. So, for example, pthreads. And pthreads is not what we prefer on Fuchsia. On Fuchsia, we actually prefer C11 threads, and we have some of our own APIs. So it was more about teaching Clang Static Analyzer about the Fuchsia-specific APIs. We also had to make some extensions to make sure that Clang Static Analyzer fully understands the concept of a handle, which is this opaque type that we use on Fuchsia. There might be more that we have to do in the future, but what we did so far was fairly straightforward.
Okay, yeah, thanks. Next question. So how do you deal with GPU drivers in Fuchsia? Specifications for embedded GPUs are usually not publicly available. So do you are you depends on the GPU vendors for the drivers? If yes, how do you keep them up to date?
Well, on Fuchsia, drivers, so first of all, I should say that this is a complicated topic. I don't think I'll have time to go into everything. There are lots of little nuances that we need to cover. But the TLDR is that on Fuchsia, drivers are just user-space programs. In particular, they are shell libraries. And so we don't even need an access to source code. This is actually something that can be completely managed by the vendor.
Okay. Mm-hmm. Next question. So is source code 100% open sourced, or some low-level code are forbidden to the public access?
So it's not actually the low-level code. I would actually say that the low-level parts of Fuchsia are mostly open source. We do have some internal bits, but those internal parts are mostly related to integration with other Google services, Google APIs. For example, as you can imagine, that if you're running Fuchsia on a Nest Hub, there's going to be a lot of integration with services like Google Assistant, and all of those integrations, all of those APIs are internal proprietary, so we don't expose those. But we always aim for starting with the open and only moving things into internal when absolutely necessary. And there wasn't a lot of cases where we had to do that. I would say though the model could be compared to what Chromium does, for example. So you can think of Fuchsia like Chromium, and there is the counterpart, which would be Chrome, which is what we ship, which is like Chromium plus some extra internal bits.
Okay, thanks. Next question. Do you use any sanitizers in production builds?
No, not at the moment. Yeah.
Okay, yeah. Next question.
I would say, I would say that the automatic version initialization is actually, so yes, we do use the Quip ASAN, which is a sanitizer. It's not, exactly the same as other sanitizers. So that one, yes. And also the automatic version initialization, like it detects sort of the same class of bugs as maybe MSAN. So kind of, yes, but we don't use like the traditional sanitizers like ASAN or UBSAN.
Okay, we are running out of time for the QA. Yeah, thanks, Peter, for your wonderful presentation. If any others have further questions, yeah, please reach out to us. We can answer as best as we can. Thank you.
Thank you. Bye.